In general, the acids we only have two types. Okay, one is called the organic, the other one is called the inorganic. The main differences between the two is that for the organic acid, those are the acids that only contain very few type of atoms. Specifically, if you see a chemical structures, okay, only contains carbon, hydrogen, and oxygen. Only these three atoms, and we call those acids as organic acid. If you contain atoms besides these three, and that is the inorganic acid. One of the most commonly seen organic acids, you will always has this functional group, COOH. When I say the COOH, what I really mean is this, COOH. Typically, you attach to some archaeal chain represented by the R here. It is the H that attach the oxygen that's going to dissociate. So if you see an organic acid, it dissociates, it becomes this RCOO minus plus H plus. So that's what happens in reality. Okay, it's actually COOH. That proton dissociate from the oxygen. So you're going to produce this and that. For example, CH3COOH, structure-wise, it looks like this. This is actually the part that's going to become an acid. This is just a group presented as R. So if you see the COOH, okay, you know the part that's relevant is this part. The other part just a archaeal chain that attaches to the acid. So using that concept, you should be able to see that this guy is going to have a structure like this. The C6O5 is a benzene ring. So it's actually a benzene ring attached to an acid. Okay, it's that acid can dissociate the proton. The protons here is not going to give you the acid. I want to actually go back and check out the structure of this guy. So let's the basic principle how you judge whether the formula you have is an acid or not. So the things you are looking for is the COOH. Regarding the inorganic acid, okay, you have two types. One is called the hydrogen halide. Basically, your chemical formula contains hydrogen and a halide atom. So if you look at the periodic table, it's on the second right of your periodic table, right? You can see it's FCl, Br, I, and At, right? So those are the halide column. So if you see a chemical structures contain the hydrogen halide, they are a very standard inorganic acid. In other words, if you see HCl, HBr, HI, HF, you know this has to be an acid. Another type of acid is called the oxy acid. If you see the sulfur, nitrogen, phosphine, or halide, this type of group appear inside your chemical structure, then there will be so-called the oxalic acid. For example, your H2SO4, you have this SO4, SO3, NO3, NO2, PO4, PO3, PO2, ClO4, ClO3, ClO2, and ClO. So those are the typical features that once you see it in your chemical structures, you know that belongs to the acid group. These are the key features. Every time when you see a chemical structures, you can predict at least it is an acid. Talk about the base. For the base, there are three different types. So it can be actually metal hydroxide, or the metal oxides, or metal hydride. So it can be O, OH, OH. General feature is actually if you see a metal, if you see an O, OH, OH, they are base. Okay, so rule number one, there are only 7 strong acids. Okay, so these are the 7 strong acids. And then for your strong base, okay, it has to be column 1, column 2, oxide, hydroxide, and hydride. So when I say oxide, it's metal, go with oxygen. Hydroxide is metal, go with OH. Hydride is metal, go with your H. If you see your 1A, 2A group associated with oxide, hydroxide, or hydride, strong base. All the others, weak base. Rule number 2 is actually this table. If you have a chemical structure that goes down to the table or goes to the right to the table, it will be more acidic. For the base, it's actually if you go more down and more to the left, it will be a stronger base. So if you look at this for now, if today I have HF, HCl, HBr, and HI, and then I ask you rank these 4 different acids based on their acidity, which one is actually the strongest? HI, right? Another example, if today I focus on this, if I have NH3, H2O, HF. Okay, if I give you 3 chemical formula, which one is actually a stronger acid? HF, right? Okay, the same concept is here. So if today I have NaOH, KOH, RbOH, which one is actually a stronger base? Right, because that's actually the one at the bottom, right? So you know that should be the answer. And again, if you have NaH, MgH2, AlH3, which one is actually a stronger base? Should be this, right? Because the things we're actually highlighting is this row, right? So if you go to the left, then you know it's actually a stronger base. So let's actually our rule number 2 and number 3, right? Actually, one for acid, one for base. Rule number 4. If today you have oxalic acid, then you can further judge based on the differences between number of oxygen and a hydrogen atom. If you have a larger differences, then you have a stronger acid. The very standard question is actually this. How do you actually judge this? This is where you're going to use the rule number 4. Okay, what you do is actually you calculate number of oxygen minus number of hydrogen. Whoever gives you the larger number, then it is actually a stronger acid. If you look at this, HClO4, number of oxygen equals to 4, number of hydrogen equals to 1. Therefore, you know this is give you a number of 3. And then you look at this, this gives you a number of 2, this gives you a number of 1, this gives you a number of 0. In this case, then you know that the acidity to arrange in this way. Can you judge the relative acidity of these 3? I hope the answer will be yes. Okay. Another very, very important thing that students get so confused is actually every time when they see this type of acids. Because one thing you are going to get tested a lot is so-called the monoprotic, biprotic, or triprotic acid. Monoprotic acid means it is the acid, when you throw it into water, it's going to produce 1 proton. What is the most famous example of monoprotic acid? What else? HF, okay. HBr, HI. How about HNO3? Okay, monoprotic. How about HClO4? The simplest rule is that if in the formula it only contains 1 proton, it has to be a monoprotic. Okay, so HClO4, monoprotic, okay? Okay, so those are the easy ones. What are the difficult ones? Let me ask you. Okay, so I give you 3 different acids here, right? One of them is monoprotic. One of them is biprotic. One of them is actually triprotic. If you really want to understand these things better, the easiest way is actually you know the structure. So I'm going to provide a structure for you, then you can actually make a judgment. Let's start from H3PO4. It looks like this. H3PO3 look like this. And then H3PO4 look like this. So remember in the very beginning when I say, okay, if you look at the acid, it is the proton associated with the oxygen that eventually become protons. So the OH is actually the minimum requirement for you to actually produce protons. With this concept, then you can actually see these things more clearly. Remember, the OH is the minimum requirement, then you can actually produce protons, right? If you look at these 3 chemical formula now, how many OH you have in this one? 1. So it has to be monoprotic. How about the second one? How many OH you have? 2, right? So this is actually the biprotic. How about this one? 3, right? Triprotic. Okay, so the way you make the judgment is actually, okay, I draw out the chemical structure. Then I have no problem to identify who is actually monoportic, biportic, and triportic. So this is actually one of the most important examples you are going to see in this chapter.